Alright, time for another DraftPhysics.com, DebatePhysics.com also. Video presentation. But again, still seeking some sort of interaction with the conventional physics, and they really don't like any conflict or any argument. They, confidently think they have the truth and it's complete enough, and they think they proved it, I guess. Even though when you ask for evidence, you're not going to get anything. Okay, you're not going to can't find it really. It's impossible to find, frankly, any useful evidence. So they could tell you, oh yeah, there's positrons, and they'll show you a picture from 1956. That could be described in lots of ways. That isn't a positron. You can go on and on all over the subjects. They just give you go do the two-slit experiment, and it proves interference. When if you do the radar experiment or you do the antenna experiment, just regular radio waves and shoot them from two different sides to a center target, you'll get the same pattern, indicating there's no interference causing the effect. But anyway. All of the crap. And so the kinetic energy is the main theory that I have been disputing over the last few years. And it's this notion that somehow increasing velocity creates more energy than increasing mass. So momentum isn't anything. And there's this idea of kinetic energy, 1/2 mv squared. And the important part is the v squared part. So I double the speed of something, I quadruple its energy. I triple the speed, 9 times. 4 times more force, I get 16 times the energy. And the one I keep arguing is show me 5 times the speed, 25 times, 25 times the energy. Absolute nonsense. No demonstration that happens in the real world. It's junk, pseudo science, and clearly, the vast majority of people, even if they don't even understand it, even if they don't know anything about it, even if they've researched none of it, will keep defending it. Because somehow, it must be true because they've been believing it for, 150 years, where they've written it in stone, and they've talked about it for 300 years, so, they must have tested it. No, they didn't test it at all. No experiments, no. So you can't show me any evidence because they never did any experiments to prove it. So anyway, that's where we are. So I'm playing Professor Dave, he calls himself, explains, and so he's pretending that he knows something. He's going to give us all some sort of insight and show us the way and guide us, through the maze of the complex science. Yeah, we'll go find the truth. And all he does is preach the truth, okay? He doesn't explain the truth. He just says, God says so. And, they just recite what they've been told. It's just a catechism sort of thing. They're just all good little Catholics, and they preach their little sermons and their little catchphrases, and that's all they have. And they really don't have any understanding in any deep level of anything. They can do some math, but that's the end of any kind of even small talent. All right, so let's proceed. Oh, I guess I should write something underneath. Some kind of something. All right, should be back. All right, so I played the internal energy video. And the recorder didn't record it. So, but there was absolutely nothing in it. So all I did, we said kinetic energy like 17 times. And yes, you could just replace all of those references to the word momentum. But he didn't say anything. He's just basically saying that a system has so much energy in it. And, we already know that. Yeah. So it was a waste of time. So you were spared a waste of your time. So all I did was keep pointing out, well, it's momentum. Heat is momentum, movement, mv. That's all there is. There's no evidence of anything else. Nothing. There's just mass moving, velocity. There's no v squared. It doesn't work. It's not real. It's a fable. All right. So let's do this video instead. This one is the 0th law of thermodynamics. So I can't remember what they call that one, but whatever. It's probably just going to be silly. All right, time for another draft. No, that's not the right. Yeah, try again. Okay. So that's the beginning of the video, I think. I had to check to see if I had failed to properly, and I had failed to properly.
Thermodynamics is a tricky subject that must be studied in chemistry, physics, engineering, and many other courses of academic study, because it has an incredible impact on the behavior of matter and energy.
So they really mess up this whole subject of thermodynamics with the subject of mixing and probability. So they end up having a conversation about how hard it is to put order back into things that are disordered. But energy really isn't ordered and disordered in any real sense, other than the fact that, yes, you can say that, light travels from a sun and spreads. And you could argue that heat in an object spreads in all directions instead of one direction. So if the heat just moved in one direction, it would be terribly useful. Like electricity, it would be very useful. But if it's spreading in all directions, it's dissipating, it's, very hard to capture. So that's, the two subjects really aren't connected. There really isn't anything about thermodynamics that leads to any kind of entropy where somehow you lose the value of the heat, because you really never lose the value of it, because frankly it's the thing pushing you into the earth, and it's the stuff melting the center of the earth. So it does all recycle.
At first, thermodynamic concepts may seem impossible to understand. But if you go over the
So this kind of stuff, when they have to preface their quantum mechanics by saying nobody understands quantum mechanics, I mean, if you're starting off by saying there's something problematic about something as simple as the transfer of energy, and basically the transfer from objects or motions that are very linear and straight line, like laser beams, to very diverse and spread out. Those are easy enough concepts to understand. That it's getting diluted. Dilution is pretty easy to understand. And that's all that's really happening, is the energy dissipates into forms that we can't see. Infrared radiation, for example. And so it's hard to follow it because we can't see it.
Basics enough times, they start to make sense, and you can continue to learn more about the subject as needed for your field of study or level of desire.
Oh, isn't that a wonderful statement? Yes, you can go on the internet and investigate subjects of physics and find out that we talk absolute shit because we don't have any evidence for the horseshit we claim to be the truth. And so if you go do that research, you will find that it's all unevidenced religion, that they never prove that electrons orbit atoms. They haven't proven any of what they have claimed to be established absolute fact. They never really tested to see if light is bent by gravity. They've done nothing. They haven't dropped 4 pounds 1 foot and 1 pound 4 feet to see if they weigh the same amount.
Knowledge. We will begin our analysis with the infamous laws of thermodynamics. Just like Newton's laws of motion.
So some of these are not very infamous. I don't even know why they're challenging. I mean, this idea of conservation, that you can't make energy. Oh, yeah, well, that sounds reasonable.
There is a first, second, and third law. But later in the development of the field, a more fundamental law was added and dubbed the 0th law.
So it wasn't established or dubbed or created by anybody. They're not accounting for it. They're just all saying ambiguously, we like it.
So let's start there. The 0th law of thermodynamics deals with thermal equilibrium, which, as we recall, describes a situation in which there is no net heat flow between two systems. The zero.
So, equilibrium is just like the Earth is at equilibrium. Obviously, it's getting hit by a bunch of energy. It must be emitting that same amount of energy. So anything absorbed has to be eventually released, or the thing has to grow. So anything not getting bigger obviously has to be at equilibrium with the stuff trying to make it bigger, let's say.
Growth law states that if two systems are in thermal equilibrium with a third system, then those two systems are also in thermal equilibrium with each other.
So that's just too idiotic, right? So they actually wrote a third law that basically says if it quacks like a duck and it has feathers like a duck and it also has feet like a duck, you could just keep go on and on. So it fits all of these categories. So the idea of saying that two things are blue and there's another thing that has every single category, every category of the being exactly the same is either one of those two things, then it also must be blue. I mean, duh.
In other words, if A is in thermal equilibrium with B, which is in thermal equilibrium with C, A and C are also...
Oh, come on. I mean, can you really believe that they wrote a law for that? I mean, so frickin' ridiculous. I mean, if you could just do this with anything, penis length, anything. Shit, if we could do it with anything. With this, how round is a button, speed of a car. I mean, obviously, if A and B are the same and B is the same as C, then C is the same as A. Gee, duh.
In equilibrium.
I can't believe they would write a law that silly.
This may seem like a trivial statement.
Yeah, it seems incredibly useless nonsense. Why the fuck? How would you possibly rationalize wasting my neurons, all right, with something this imbecilic? 3 equals 3 equals 3. Yeah, I get it.
But it is an important one, because it means that two objects at the same temperature will not exhibit heat flow when they come into contact with one another.
So again, I don't know why the fact that C equals A or B means that A and B can't do anything. But I mean, we already established that they're at thermal equilibrium, so what's the point of it? Of course, there can't be any change because they're at equilibrium. So they've reached a state, okay, that isn't pushing or pulling. So they can't change in any way.
This marks temperature as the indicator of thermal equilibrium. If two...
All right, so that's really bad, too. I mean, the indicator of thermal equilibrium, that's not what it's indicating. So, this is just terrible nonsense.
Objects are in thermal equilibrium with thermometers that read the same temperature, the objects will be in thermal equilibrium with each other.
Yeah, things with the same temperature are the same temperature. Can you believe it? Isn't that amazing?
Which therefore allows us to gather all kinds of thermodynamic data in our laboratories.
So I don't even know what that could possibly mean. What is it? What does taking something's temperature have to do with thermal equilibrium? This is just such nonsense.
In studying thermodynamics, we must also learn certain definitions. We will want to be able to define a system as the collection of objects we are examining, while the surroundings represent the environment surrounding the system, which is technically the rest of the universe.
So, yeah, and what is this? Again, this will have nothing to do with anything, because we know you're just going to capture things that are definitely going to get colder and hotter, and they're going to change over longer periods of time. And most of the time, you're going to try to do your experiment, like if you're going to make a sword out of steel or something. Yeah, you don't wait for the steel to cool down to try to manipulate it. Duh.
Some systems allow heat to flow in and out. These systems have diathermal walls. Some systems do not allow heat to flow in and out. These systems have adiabatic walls. no system can be truly adiabatic.
There you go. I was just going to say, well, there's no such thing anyway. So, yeah, you can only do your best to reduce the amount of thermal activity, but you can't get rid of it because it's in these two forms, and one of the forms is like gravity, and you really can't make a gravity shield.
But it is a useful approximation when we do calculations involving systems that permit only negligible heat transfer.
So, I mean, they're too ridiculous, right? So, yes, you have to do your experiment while the thing's in the condition, you know, you're hoping it to do the experiment in. Maybe it can change by a couple of degrees, and that's okay. I mean, this was just a waste of time. So, these two videos were just junk. Big titles, very small product.
With these definitions out of the way, we can move on to the first law of thermodynamics.
So what definition do I need there? You know, you have containers that are well insulated, containers that aren't so well insulated. Do I really need to know those silly words? No, I don't need to know any of those silly words. Ugh, what a waste of time that was. All right, try again. All right, so he's going to be telling us about the laws of thermodynamics when they don't understand that gravity creates momentum and heat. So it emerges out of the function of gravity. So, you know, same thing as cause. So it basically creates an origin of momentum. Something is in space, it will gain motion and momentum, it'll crash into the earth, it'll induce pressure, and the center of the earth, from all of the weight on the earth, all the mass moving towards the center, will be crushed, creating huge amounts of heat and energy. So gravity creates energy. It makes it appear where it wasn't. Fact. So somewhere, if you're going to do any of this conservation crap, you have to explain how the energy goes into the bent space. You have to explain how the bent space is fueled, or else you have a perpetual source of new energy in the universe. In every object in the universe is creating new energy. So obviously bent space is a silly answer because there is no mechanism to convert the heat back into, gravitational motion. And the correct mechanism would be the sensible one of recognizing that, yes, there is thermodynamic equilibrium in the universe, and gravity is putting the energy back into things like suns, so it can be radiated out of them, and that every material object is participating in that process of consolidating heat and then releasing it.
The first law of thermodynamics, popularly known as the law of energy conservation, when examined more rigorously, actually...
So they don't rigorously examine anything. Again, they haven't dropped 4 pounds 1 foot, 1 pound 4 feet. They haven't, with 400 times better resolution from space, 400 times, not 4, not 40, 400 times. They have, and the Eddington experiment doesn't need an eclipse when you do it from space. So it's a 5-minute experiment, and we're supposed to believe NASA's never even tried it. The experiment that made Einstein famous, and they haven't even tried to do it to confirm those results from 1919. Amazing.
Outlines the relationship between internal energy, work, and heat.
So internal energy is baby talk. There's and work and heat are the same thing. It's just energy. And the first law of conservation is that if you're going to create motion, it had to come from something. Something had to give it motion.
Which from now on will be represented by the letter Q. The law can be stated as an equation where delta U equals Q minus W.
So the W is silly because we know everything's work, including heat, so it's just a waste of time.
This means that the change in the internal energy of a system will be equal to the energy transferred to or from the system as heat.
So again, and it can be, the energy isn't always in the form of what you would call heat, so it's just kind of silly. But yes, you can have motion as big things, or you can break the big thing into a bunch of little things, and you have lots of motion, and one will measure a temperature and the other one won't. So, so what? You can, you take a heated piece of steel and you put it in water. The water will increase its temperature. You'll be able to read the temperature, all that kind of crap.
Minus the energy transferred to or from the system as work. And all of these quantities will be measured in joules.
And they can be measured in newtons or watts, so it doesn't matter.
Because of this law,
they can be converted into almost anything. Calories.
We can outline a few different types of processes that can occur.
I mean, that's one of the things to find fault with physics, is they have all of these different ways to describe the unit of exactly the same thing. So that's, horsepower, lots of different ways of describing the same thing. Pressure, weight, force.
If a process occurs where there is no change in volume for the system, that means that no pressure volume work can be done on or by the system.
So again, I don't know in what context volume would be significant or meaningful. If you're falling in gravity and I change your volume, it's not going to change anything about how much work you're going to do.
So work is zero. In such a case, delta U...
I mean, change your volume in the sense of just separate your atoms so they take up more space.
Equals Q, and any change in internal energy must be the result of heat transfer in or out. This will be called an isovolumetric process, meaning no change in volume. An example would be a bomb calorimeter, where a combustion reaction produces a change in temperature, but the rigid walls result in no change in volume.
So I guess they're saying that this is one way they can measure how much energy or fuel something has. So again, this is the catch, right? Because if I wanted to measure how much power a unit of gunpowder has, depending on what size bullet I put in the gun, I can get very different answers for the kinetic energy. So it's a little bit dangerous as an experiment. But this goes back to Joule and basically recognizing that, yes, if you can insulate a substance and then you can put energy into the substance and consume all of the motion that thing has in the substance, that the substance temperature will increase proportional to the amount of energy. So that's all perfectly valid. But I don't know exactly what this has to do with conservation, but whatever.
If there is no change in the temperature of the system, there cannot have been any change in the internal energy of the system, since these two values are proportional. Delta U will be zero, which makes Q equal to W. This means that any heat transferred into the system is used by the system to do work, rather than increasing the internal energy of a system.
So obviously nothing will ever survive doing 100% work and producing no heat. So there's almost nothing that's that efficient.
This is called an isothermal process, meaning no change in temperature. An ideal version of a car engine would be an example of this, as the pistons ought to convert all of the heat energy from the combustion reaction directly into expansion work that moves the car.
And obviously it doesn't work, so what's the point of pointing it out? Because there's no ideal engines.
If there is no heat transfer, Q will be zero, and delta U will equal negative W. This means that the internal energy of a system changes as a result of doing work on its surroundings, or the surroundings doing work upon the system.
I mean, I don't even know why he brought up a combustion engine, because the fact is if you don't dissipate the heat, the engine will fail. So it's like you can't keep the heat in the location you need it to stay in, and therefore you have to get rid of it because it will do damage.
Such a process will be called an adiabatic process, meaning no heat transfer. We can see this in certain processes in Earth's atmosphere as masses of air change position due to pressure differences.
So again, all of these are just transfers of motion, okay, between big things, little things, and other little things. This all needs to be understood. Doing this idea of qualifying these as different events when they're really not that different. It's no different than understanding the difference between sandpaper and water. Yeah, they're different kinds of friction, but they don't need different categories.
And if Q and W are both 0, meaning there is no heat transfer and no work done, there can be no change in internal energy, and this must be an isolated system.
Yeah, there was no change in internal energies, and it was an isolated system. So again, it's just, I'd say that was said poorly.
Hopefully these scenarios make some intuitive sense, because we will frequently use this equation to do calculations.
So for what cause, I can't even imagine why you would bother with this idea of internal energy as meaning anything. All you really want to know is how much motion is there and how much heat is there. So, and it all has to add up. It's all momentum. So if you just say it's all momentum, and you just say how many little things are moving and how many big things are moving, and what velocity are they moving, there, I've done my job. That's all there is. There's just mass moving. I just have to calculate from one moment to another how much mass is moving. And if it's the same amount of mass moving, then I know I've conserved and it's an isolated system.
We will also need to define the signs of these quantities in order to use this equation properly. So let's note that when heat is absorbed by the system, Q will be positive. If heat is lost by the system, Q will be negative. If work is done by the system, like an expanding gas, W will be positive.
So expanding gas is doing work? Okay, so who knows?
Positive. If work is done on the system by the surroundings, like gas compression, W will be negative. If there is no transfer of heat or no work done, these values can also equal 0, as we have previously discussed.
So I argue that this is all useless. So whatever this crap is, I don't think it's ever going to be used in any effective formulation. It's not really going to help you. So these are the same people, okay? They do a ballistic pendulum experiment. So here they talk about all this crap, and they haven't even bothered to measure the temperature of the internal temperature of the ballistic pendulum. So we know they can only, they are losing 99.94%. That much. 99.94% of the kinetic energy. And they can't even bother to stick a thermometer in the gel or the clay or whatever they're shooting the bullet into to see how hot it got. That's how bullshit this physics is.
When doing calculations, make sure that you use the correct signs for these values, or the math will be incorrect.
Well, whatever math he's going to do with this concept of internal energy is going to be useless.
For example, if 100 joules of compression work is done on a system, and as a result, the internal energy of the system increases by 74 joules, how much of the energy is transferred as heat and in which direction?
Yeah, and I bet they don't do this experiment. Yeah. Well, what are you compressing? So he doesn't even use something that you could say, okay, you're going to have something in a press and you're going to press it in both directions. Obviously, this can only happen inside of a cylinder or something where you have a piston. And then you can compress the gas and then find out how much hotter it gets.
Take our equation and rearrange to solve for Q, which will be delta U plus W. Then we can plug in positive 74 joules for delta U, since internal energy increases, and negative 100 joules for work, since work is being done on the system. And we should get negative...
So I don't know what the 100 work, where did you measure that? 100 joules of work is done on a system. What does that even mean? Yeah. So obviously it's just saying that you have to have the conversion here. So if How much energy is transferred as heat? So he's saying it's negative 26 joules? Yeah, no, I don't think so. But anyway.
26 joules for heat. This means that as 100 joules of work is applied to the system, only 74 go towards increasing the internal energy of the system, while 26...
So how are you measuring the internal energy of the system? Do you see what's flaw here? Is that what's the internal energy of the system? What are you measuring? Except temperature. What else can you possibly be measuring? How much work you did on the system? How are you measuring this work on the system other than measuring temperature? No. Pressure? I don't know. Air pressure?
joules are lost as heat dissipates out of the system. These kinds of calculations will happen a lot in thermodynamics, so let's check comprehension.
Yeah, what a pile of crap. So I don't think these will relate to anything real, so I don't think any of this will certainly be tested. So we'll just call that a pile of nonsense and a waste of time. So he took a good subject, which is the conservation of heat in the universe. That's the first law of thermodynamics. That, there's no way to undo this momentum trail. So it always has to be about the MV, and you always have to have it. You can make little things go fast, or you can have big things going slow, but the amount of M and the amount of V has to be the same total. And so you can have little things with little M's and big V's, or you can have big things with big M's and little V's, but in the end, you can't make energy and you can't destroy energy. And energy is heat. And so you're basically saying that thermodynamically, the universe can't make heat and it can't destroy heat. And frankly, heat, okay, is what gravity is. All right. It's the differential you end up with by pushing heat into the center of the earth and delaying essentially the amount of heat we get hit by from the universe versus the heat coming through the earth, because a bunch of it's stored in the center of the earth. It's temporarily delayed heating the earth, and therefore it doesn't push you back. You're not at equilibrium. So gravity breaks your thermal equilibrium with the universe. If you're alone in space, the temperature of the universe hits you from all directions. If you're on the earth, the temperature from the universe is high, where up there, and the temperature from the earth is a little bit lower. That's the sensible way to understand it. All right. So that'll have to be enough of a video. Yeah, I don't know. This one got broken. These are pretty crappy, frankly. So he got kind of lazy and, in my opinion, kind of loose with these videos. I don't know what the rest of them are going to be this poor, but this was a pretty poor description of thermodynamic conservation. Heat conservation in the universe. Motion conservation in the universe. Quantity of motion conservation in the universe.